Hi everyone, lesson 2.5 is going to focus on logarithms. Okay, so logarithms also work with our concept of exponents. And most of you, if not all of you, have probably seen on your calculator, there's two buttons. Okay, there's one that says log, okay, L-O-G, and usually directly beside it, there's a button that says ln, and that's LN, not IN. Okay, a lot of students think it says in. And we're going to talk about log and ln now, log being a logarithm, ln being what's called a natural logarithm, and we'll get into what some of those differences are. But what logarithms are used for is to actually find an exponent that a base has to be raised to produce a given number. Okay? So for example, okay, if we have the number 64, that is equal to 2 to the exponent 6. Okay? So for a logarithm, what that means is that if you were to use the log button and were able to choose your base, you would write your base here is 2, and the number you would input is 64, and that would be equal to 6. So these are interchangeable. When you use the logarithm button on your calculator, I'm going to tell you some of the limitations of it, but the answer that comes out when you press that button is the exponent that your base has to be raised to give the number that you inputted in. Okay, so as one example, okay, so 6 is the logarithm of 64 if the base is 2. 3 is the logarithm of 64 if the base is 4, and that's because 4 times 4 times 4, or 4 to the exponent 3, is 64. Okay, so you're solving for that exponent when you use the logarithm button. Lastly, 2 is the logarithm of the same number 64 if the base is 8, and that's because 8 squared is equal to 64. Okay, so in each of these instances, it's always the exponent that you're solving for. So I want to go directly into a few examples. Okay, I want you to pay specific attention to the notation for a log function. So we have log, which is the same as how it looks on your calculator. Here we have the base, and here we have the final number, which you could call the power. Remember, you had a base raised to an exponent, and that was equal to your power, right? So 2 to the exponent 3 is equal to 8, okay? So this as one piece, or the 8, are known as the powers. The number 2 is the base, and the number 3 is the exponent. So all we're doing is rearranging this for a logarithm, because we're not solving for the number 8. Okay, we're not putting it in our calculator and putting 2 to the exponent 3 and getting 8. What we're doing is we're putting the other two numbers in instead, the 8 and the 2, so we can figure out this number 3. We want to know what the exponent is. Basically, this allows us to find a growth rate. Okay, so a lot of exponential logarithmic pieces are used for growth rates. Okay, how fast your house might grow in a market if the market is booming. Okay, is a good example of that. So using this kind of what I've said, let's now look at some examples. So we have the log of 8 with the base of 2. And I'm going to tell you that that answer is equal to 3. The reason for that, remember, you're trying to find an exponent. So what you're trying to find is 2 to some exponent, we'll call it x, is equal to 8. The number that your calculator will output is this value of x. So what we're looking for in a logarithm is what exponent does 2 because that's the base, have to be raised to arrive at 8. Okay, so we know that 2 times 2 is 4 times 2 is 8, or 2 to the exponent 3. Okay, for some people, this can be a difficult concept to think of, and that's why it's good to try each of these as practice. So for B, we have log base of 8 of the number 8, okay, meaning 8 to some exponent x has to be equal to 8. Well, we know that the exponent here needs to be 1, right? Because 8 to the exponent 1 is the same as writing just 8, right? These are the same number. So this can't be 0, or 2, or 3, or 4, right? Because it's not going to be equal to 8. So this logarithm would simply be 1. Part C, we have log of 16, and the base is 2. So 2 to some exponent is equal to 16. So in this case, 2 times 2 is 4, times 2 is 8, times 2 is 16. So that's the same as 2 to the exponent 4, right? Because there's 4 2's here multiplied together, meaning that this logarithm would output an answer of 4. Okay, because remember, it's trying to find the exponent. Example D is the log of 16 and the base is 4. So again, 4 to some exponent is equal to 16. So we have simply 4 times 4, and that's equal to 16, right? So there's 4 2 times, which is 4 squared. So our logarithm here, our solution is 2. So I'm going to write these in a different color for those of you that are following along, so you can see the distinction versus just my side work. So E is similar to B. Okay, we have the log of 16 and the base is 16. So we have 16 to some exponent is equal to 16. Again, that must mean that your exponent is 1, right? Because 16 to the exponent 1 gives you 16. F, we have log of 2, or log of 1, sorry, with a base of 2. So 2 to some exponent x is equal to 1. Remember back from our exponent lesson, how do you get a solution of 1? Okay, remember, any number to the exponent 1, so to the exponent 0, I mean, is equal to 1, meaning this logarithm must be 0. Okay, again, I'll do it in blue. Logarithm of 2, or of 1/2 with a base of 2, okay? So we have 2 to some exponent x is equal to 1 divided by 2. Now this one gets a little bit trickier. Remember, we talked about negative exponents. So this can be written as 2 to the exponent 1, okay? And remember, if you move from the numerator to the denominator or vice versa, you change the sign of the exponent. So that's the same as 2 to the exponent negative 1. Meaning that x, okay, what we're looking for must be negative 1. Okay. Example H, log of 100 and the base is 10. Now this base of 10 you're going to see is very important because the log button on your calculator, unless you have the more expensive sharp version, you only have one log button and it is always base of 10. Okay, so all these other examples, you might have tried putting them in your calculator and they wouldn't have worked because they're not under a base of 10. We're going to see why that's important in a little while. So we have the log of 100, the base is 10. So 10 to some exponent is equal to 100. So 10 times 10 gives you 100, meaning that this logarithm must be 2, right? Because 10 squared is equal to 100. Example I, we have log of 1,000. Again, the base is 10. So 10 to some exponent x must be equal to 1,000. We have 10 times 10 is equal to 100 times 10 is equal to 1,000. So that means that 10 to the exponent 3 is equal to 1,000. So our logarithm here is equal to 3. Our final solution, okay, log of 1 divided by 100, the base is 10. Remember, we have 10 to the exponent x is equal to 1 divided by 100. Now remember back from question H. 10 squared is equal to 100. So we can write this as 1 divided by 10 squared. Now remember, we can move that 10 to the numerator if we change the sign of the exponent. So that's equal to 10 to the negative 2, okay? Meaning that our solution here is negative 2, right? Because x must be equal to negative 2. All right? So I put this slide in here as a summary of what I've talked about. I want you to understand clearly how, a power with a base and an exponent relate to a logarithm, okay? So if you have the number 8, you can write that as 2 to the exponent 3. Now if you wanted to write this as a logarithm, okay, you would have the exponent on one side, okay, 3, and that's equal to the log of your base, which in this case is 2, and your number here is your power, okay? So the number you would input in your calculator that you're finding the logarithm of. So to write this in a basic form, if you have y, or some number, is equal to a to the exponent x, so some base a raised to an exponent x, if you flip that to its logarithm form, that exponent x is equal to the log of y, okay, the number you started with the base of a, okay, whatever that base might be. So looking at two more examples, if 25 is equal to 5 to the exponent 2, or 5 squared, then you take your exponent 2, and that must be equal to the log of the number you started with, 25, with a base of 5, okay? So it's the base of your power. If 81 is equal to 3 to the exponent 4, then your exponent 4 must be equal to the log of the number you started with, 81, with a base, okay, of 3. All right, so that it's just different notation where you're not trying to find the final number, okay? You're trying to find the exponent it has to be raised to. And there's a lot of very, very useful applications for where logarithms can be seen. Okay, so now let's practice this. Okay, I'm going to give you a value and a base. Okay, and I want you to write them in both exponential and logarithmic form. So take some time to fill this out. Pause this video if you choose to. Fill them out yourself, and then watch the solution. Okay, so let's look at the first example. We have a value of 32, and the base is 2. Okay, so we know in exponential form, 2 to some exponent x is equal to 32. In logarithmic form, remember you're solving for the exponent. So you have the logarithm, your base is 2, and your value is 32. And that's equal to some value of x, okay, some exponent. In this case, the value of x is actually 5, but I wanted to show you this for the purposes of our demonstration. Next, we have a value of 256 and a base of 4. So we have 4, again, to some exponent x must be equal to 256. Or the log base of 4 of the value 256 has to equal x. Okay, once again, just writing this in different forms. Again, we can solve for x here. It's actually 4. Okay, just to let you try both ways. And for a value of 6 and a base of 36, okay, we have 36 to some exponent x must be equal to 6. Writing this in logarithmic form, we have the log. Again, your base is 36 and your value is 6. And that has to be equal to that value of x. Now, the answer to this, once again, you can figure out is 1/2. Or, in other words, the square root of 36 is equal to 6. Okay? Because remember, you can write your square root as 36 to the 1 divided by the order of this root. Okay? And since the order is not shown, it's inferred that it's a 2. Okay, just to show you, I want to show you how these lessons all correspond to each other and are all just different pieces of the overall puzzle. So you've seen that so far we've used logarithms with different bases, 2 log of 4 of some number, let's call it 16, log of 10, number 100, where the base is always different. Now, remember another thing I told you at the start of this lesson, most of your calculators cannot directly calculate any logarithm without a base of 10. Okay? Now, what I mean by that is your log button on your calculator doesn't have a base. Okay? So for almost all of you, unless you have a more expensive calculator, we'll just have a log button that looks like that. Now, what that means is a base of 10. Okay, so your log button on your calculator only does base of 10. Now, that reminds me of, the square root button, okay, where it just does the square root or order of 2. It's the same function that the log button is, okay, where it only does base of 10. So that's why if you were to put log of 8 in your calculator or 16, you're not going to get the answers that you would get here if you calculated out with a base of 2 or a base of 4. So anytime you put a number in your calculator and you press the log button, what it's doing is doing the log with the base of 10 of whatever number you put in. Okay, so let's use 8 as an example, okay, following along with that. It's assuming a base of 10, not the base you're seeing in the question. All right, so this is what's known as a common logarithm because that's the most common one that you're going to see, okay? So it's very important to keep that in mind, okay? So when we have questions on a test that are not in a base 10, okay, you can't use your calculator for it, okay? You have to be able to determine that yourself. So I'm not going to give you ones that are decimals, that'll usually be whole numbers. The other thing to keep in mind is, remember, this button doesn't have a 10 showing. It's inferred that it's base of 10. Similarly, when you see questions, okay, that just say the log of 10, okay, with no base written, it is inferred, you have to infer that the base is 10, okay? So when it's not shown, you always assume that the base is 10, okay? So it's a very important thing to keep in mind. So let's look at some examples of this, okay? So I'm going to show you some common logarithms. you'll see that none of these show a base. And what that means is that the base is 10. Okay, so when it's not shown it's a base of 10, you can evaluate these using the log button on your calculator. And we will go through this in class and tutorial, how to use the log button on your calculator. Okay. So we'll start with A here. Okay, log of 10, that's equal to 1. Okay, because again, you're finding the exponent. Because remember, the base here is 10. So 10 to the exponent 1 would give you 10. For B, okay, log of 0.1. If you put this in your calculator exactly as it shows, either by pressing log, then typing in 0.1, or for some of you, you might have to type in 0.1, then press the log button, okay? Just like with the root functions, it depends on your calculator. Now the answer that's going to come out is -1, okay? Because 0.1 can be written as a fraction, as 1 divided by 10, which remember you can write as a negative exponent as 10 to the exponent -1. Okay? Example C is where we start to get into different numbers, numbers that don't evenly divide. Now, if you were to put log of 72 in your calculator, this long decimal would be the number you would arrive at. 1.857337 continuing on. The reason for that, remember, it's a base of 10. So what that means is 10 to the exponent 1.857337, that long decimal, would give you a value of 72. Okay, it's very important to understand this when it comes to your calculator. So let's look at a few more examples. And these ones, I don't have the solutions shown, so I do encourage you, like I have in previous lessons, pause the lesson now and try these. You can do them either yourself if you want to, or you can put them in your calculator. I have no problem with you putting them in your calculator because these are all base of 10, right? Because there's no base shown here. So we'll start with log of 1,000. So for this one, we have 10 times 10 times 10 gives you 1,000. Or if you put this in your calculator, you should arrive at 3, because 10 to the exponent 3 is 1,000. For B, okay, log of 1 million, again, you can put that in your calculator by typing in log of 1 million. You'll get an answer of 6, and that means 10 to the exponent 6 is 1 million. But you can put that in your calculator to check your solution. Next, we have the log of 0.0001. And again, in your calculator, you get -4. And what that means is 10 to the exponent -4. If you put that in your calculator, you would get 0.0001. Next, we have the log of 1. Okay, put that in your calculator, you get 0. And that's because 10 to the exponent 0 is equal to 1. Remember, any number to the exponent 0, unless the base is 0, but any number that's not 0, gives you 1. Part E, okay, you're not going to get a nice even number. Okay, this is the decimal place. So if you put this in your calculator, you log of 147.2, you get 2.1679, and it continues on. And that's because 10 to the exponent 2.1679 continuing on would give you 147.2. Okay? The next log I want to talk about is natural logarithms. So natural logarithms are actually my favorite one to use. They're, in my opinion, the easiest option you have, even though the base will seem a little bit more complicated. So for natural logarithms, we often look at an important mathematical number. Okay, it's known as E, or Euler's number. And what Euler's number looks at is it's looking at an exponential function where you start with 1, okay, and you add 1 over n, okay, and raise it to the exponent n. And what you're doing is looking at what this value is, okay, what this piece is, as your value of n approaches infinity. And it actually comes out to a number, an irrational number, so similar to pi in that it continues on as a decimal, with the first numbers being 2.7182818. 1828 keeps going, okay? And it's an exponential function. And what the natural logarithm is when you take the log, but your base, remember it was always a number, whether it was 2 or 10, okay, when you're talking about your calculator. Instead, we're going to put the base of e, okay? So this is what the ln button, that looks like ln, okay, or some people think it's called in, but it's actually ln. That is the button usually directly beside the log button on your calculator. And ln, the reason it's beneficial is you don't have to stop and think about what base you have. Okay, so for the log function, you can only use your calculator to take the log of, let's say, the number 10 if your base was 10. Okay, so if you were given a question that had log with a base of 2, okay, you couldn't use your calculator for that. Ln is different. You don't have to worry about whether or not your base, okay, is correct when you're using the ln function. And we're going to see that the same rules apply to log functions as they do to ln. Okay, so this is, like I said, a number like pi, and it's for an exponential growth function, a very common one that you see being used. Okay, so the difference with ln is that you need to use your calculator for it. I will never ask you a question with ln where you have to figure it out yourself. There's a couple specific ones that you're going to see that you can do, or just know in your head that they're true. But in the meantime, let's just look at doing a few examples. So our first one is ln of 2. Okay. Now remember, for those of you looking at your calculator, you have two options. For me, okay, I have two lines in my calculator, so I press the ln button, then I press the number. So in this case, for example, A, I would then press 2. So if you do that and I press ln of 2 and press equals, I get this number. Now some of you might have to press 2 and then press the ln button. Okay, so again, make sure you experiment with those to determine which one you use most often. Okay, so if we take the ln of 10, okay, for example, B, again, putting it in your calculator, you'll get 2.30, we'll call it 2585, and it keeps going. Okay, ln of 3000, again, 8.00, we'll call it 006, but it continues going. Ln of 0.5 is a negative number actually because it's less than 1, right? So you're going to have a negative exponent here. So you actually get negative 0.6931, and it continues on. The next one is the ln of 1. Okay, so remember, when we had any number, 2 to the exponent 0, okay, any number was equal to 1. Well, in this case, our base is e. So for each one of these, we have e raised to some exponent. And just like every other example, e to the exponent 0 is still 1. So if we take the ln of that, okay, we're going to get 0. So I don't even have to put that one in my calculator. That's just one to know, okay? For f, ln of 0.0125, you get negative 4.382, and it keeps going. The next number, you're going to see that you're going to get a number close to 1. And the reason for that is e is actually a number, and it's 2.71828, and it keeps going. Okay, so if we put this in, you're going to basically get 1. Okay, you get 1.0007063. So if you had the full number of e, you would actually just get 1. Okay, so that's what leads me to example H. The ln of e is simply 1. Okay, that's actually an identity to know about ln. And the reason for that is, remember, ln is actually log of e. In this case, it'd be the number e. Okay, remember, that's what the ln function actually is. So if you're writing this, it's got to equal some number. But what this means is e to some exponent x is equal to e, right? Because you're trying to make it equal to this number here. So your value for this x must be 1, right? Because you just have the number e. So that's why ln of e is equal to 1. So my next topic, this is one that throughout my education I used extensively, these relationships. And these apply both to log functions and ln functions, okay? So I'm going to focus here on natural logarithm. Again, that is my preferred way when I'm dealing with any of these types of relationships. But they apply whether or not it says log here or ln, okay? So our first one is if you have two numbers within a ln function. So if you're taking the ln of a times b, let's say the ln of 3 times 2. The first relationship says that's equivalent to the ln of the number 3 plus the ln of the number 2. Okay? Where that's useful is when we start talking about equations and we have something like the ln of 3x. Okay, we don't know what x is, but we want to solve for it. So we can first break it out by taking the ln of 3 plus the ln of x, okay, by separating those out. That's kind of where it's useful. There's more relationships where you'd actually be able to solve for x, but that is where you'd really see it. Now this would be the same if you were to do it with log, okay? So if you had the log of a function, a and b, this is equal to the log of a plus the log of b, okay? Obviously, this would depend on if the base here is 10, okay? The base is on the right-hand side would then be 10, or alternatively, let's see if I can erase all of these without erasing the log. You know, this could be the base of 2, whatever it might be. But the same function still applies. This is why I like ln better. It doesn't matter. I don't have to show you a base, okay? And because it's used so much, your calculator has the ln button built in. So it's not like you have to do extra steps on your calculator. You actually have less steps. The next relationship is when you have two numbers divided by one another. Okay, so the ln of a divided by the ln of b. And it's equal to the ln of the numerator minus the ln of the denominator. Okay, so keep that in mind. There's a minus here when it's division and a plus here when it's multiplication. So if you had something like the ln of 3 over 2, it's equal to the ln of 3 minus the ln of 2. Okay, unlike the first example, remember that minus. Okay. And just like in the past, if this still works if you have the log of 3 over 2, it would be the log of 3 minus the log of 2. Okay. The last rule, which is in my opinion the most important one, because it really allows you to solve for a lot of much more complicated expressions, especially expressions where you're trying to solve specifically for an exponent. So if you have the ln of some function raised to an exponent, okay, so let's say the ln of 3 to the exponent x, this rule allows you to move that exponent behind the ln and multiply it by it, okay? So this becomes the exponent x multiplied by, and now just the ln of 3. Okay, and ln of 3 you can put in your calculator. This is the most in my opinion, useful of the three rules. All three of them are used quite extensively, but this one really allows you to solve for that additional exponent, and that's a very important piece. Okay. So we're going to look at some examples. Okay. And these first ones, I want you to put both of them in your calculator. Okay. So if we had the ln of 15 times 36, if you were to take the ln of 15, okay, you arrive at this number here. And the ln of 36, you arrive at this number here. Adding those two together, you get a number of about 6.29, and it keeps going. Now, I want you to show you this because I want to show you that the rule works. That was using our rule, right? The ln of 15 times 36. So we're allowed to break those apart and add them up. So the ln of the first number, 15, plus the ln of 36. But let's say you multiply those together. 15 times 36 is 540. So that's the same as writing the ln of 540. So now put that in your calculator and you'll see that you arrive at the same number, okay? Depending on your rounding, maybe your last couple decimals might be a little bit different, but that's just because of rounding. That's not because the rule doesn't give equivalent results, okay? So now let's look at another example. So we're going to use our calculator to evaluate the ln of 5,000 divided by 1.045 using two methods. First, the laws of logarithms that we just talked about, and second is without it, if we just multiply those numbers out. So for A, we have the ln of 5,000 divided by 1.045. And if you break that out, those are divided by one another. So that's equal to the ln of the numerator, 5,000, minus the ln of the denominator, which is 1.045. So using your calculator, the ln of 5,000 is 8.517193, and it keeps going, minus the ln of 1.045, which is 0.044017, and it keeps going. So if you subtract these, you can hear my key buttons probably in the background. You get 8.473176, and it keeps going. So that's using our rules that we know. If we decided to just divide this out right from the start, we have the ln of 5,000 divided by 1.045. So if I take 5,000 divided by 1.045, I get the ln of 4,784.66, and then it keeps going, 88995. If I take the ln of that, again, I get 8.473176, and it keeps going. So the number stays the same. Okay, so that's just showing you once again that these rules of logarithms work. Okay, our last example is I want to show you it, okay, if you have something like this with an exponent. So we're going to use our calculator to evaluate the ln of 5 to the exponent 7, again using the laws of logarithms and without it. So for A, we have the ln of 5 to the exponent 7. Now remember, if there's an exponent in here, you can move it behind the ln and multiply it by it. So this is the same as writing the exponent, which is 7, multiplied by the ln of what is remaining in there, which is just the 5. Okay? So if I do this, I get 7 multiplied by the ln of 5, which is 1.609438 approximately. So if I multiply that by 7, I get 11.266 approximately, and it keeps going. Now instead, I could just take the ln of 5 to the exponent 7, and 5 to the exponent 7 is the same as the ln of 78,125. So if I use my log button on my calculator and find that, again, I get 11.266, and it continues on. Okay, so once again, you see, and again, this is using numbers, right? So a lot of you are going to say, why would I use rules for that? Well, the reason you do that is if you're trying to solve for something. If this said the ln of 5 to the exponent x, how are you going to solve that? Right? There's no way for you to solve that without being able to use that rule in writing this as x times the ln of 5. This allows you to isolate x by itself and solve it. That is really where these rules are so important. Okay? All right, so that's it for this lesson. Please try these exercises, bring them to our class or tutorial sessions if you have any questions. And that's it. Thanks, everybody.